Example 33B.1. A single slit diffraction experiment is set up with light of wavelength 420 nanometers, incident perpendicularly in a slit of width 5.1 microns. The viewing screen is 3.2 meters distant. A. Draw a picture of the situation that shows angles theta sub n and d and delta r divided by lambda. On the screen, B, what is the distance between the first and second diffraction minimas from the center of the diffraction pattern? C, what are the widths of the central diffraction maxima and the first secondary diffraction maxima? Picture-wise, what does the diffraction pattern look like? In other words, how many minimas and maximas are there? The path difference equation, A sine of theta equal nd lambda, the maximum value of nd is then equal to the diffraction parameter. Putting in these values, we are getting 12.1 for maximum d, so that means there are 12 full minimas. On the intensity pattern, I find that with only drawing half of it, I have 12 minimas, and this 0.1, this little bit right here is that 0.1 that starts to move up above from the 12th minima. Since intensity is a function of alpha, what are the alpha values? Writing out alpha, pi a sine, divided by lambda, then tells us that alpha must be nd pi. So writing out the phase, I then see that for nd1 it's pi, for 2 it's 2 pi, etc. all the way down to 12 pi for the 12th minima. Let's draw a picture of the experimental situation. So I have violet 420 nanometer light impinging on a single slit that has a slit opening of 5.1 microns. The distance to the screen is unknown, and then I produce this diffraction pattern. Here's my central max with my first secondary maxima, and the location of the first minima is y1, the location of the second minima is y2. Angular locations of the first minima is in green, which is theta 1. The angular location of minima 2 is in orange, theta 2. A small typo, I do know what the screen distance is, it's 3.2 meters. A small angle apply. Since A is 5.1 times 10 to the 6 meters versus D, which is 3.2 meters, A is much smaller than D, and therefore does apply. I will be using a non-small angle calculation so that you could see the application. Angular position theta is determined from the path difference equation. In other words, sine of theta is equal to nd divided by the diffraction parameter. Where the diffraction parameter we already computed, which was 12.1. The first two minimas, I get the angles of 4.72 and 9.48 degrees. I know that the screen location of these minimas is y of n, which is equal to d tan of theta of n. Computing y1 and y2 here, putting in these angles, I get that it's 0.264 meters for the first one, and the second one is 0.534 meters. The distance between the first and second minimas is then given by delta y, which is equal to y2 minus y1. Computing this number, we get 27 centimeters for the distance between minima 2 versus minima 1. Otherwise, this is just the width of the first maxima. So if this is y1 and this is y2, then between 1 and 2 is this width of the first maxima. As a comparison, let's use a small angle approximation now to compare with the previous calculation. If sine of theta is approximately tan of theta, then they're equal to theta. Then the path difference equation is now a theta equals nd lambda, and the minima location, y of n, is now d theta. The location of the minimas then is nd times big D divided by the diffraction parameter. For the first two minimas, ND equal to 1, I get Y1 equal to 26.5 centimeters. For ND equal to 2, I get 52.9 centimeters. Comparing the results between non-small and small angle approximations, we could see if we compare them, we get a 0.38% and a 0.94%, less than 1%. So the small angle approximation is a good approximation.
Example 33B.2. A slit width 0.24 millimeters is illuminated by 540 nanometer light. The diffraction pattern is observed on a screen that is 3 meters from the slit. A. Draw a sketch of the diffraction pattern that includes all the minimas and maximas. B. What are the approximate locations, of course relative to the central max, and relative intensities of the first, second, and third secondary maximas? At what location is the relative intensity half its value for the central maxima? To sketch a complete diffraction pattern, we must compute the n value. This is from the path difference equation. So if I look at the maximum value of nd, it's equal to the diffraction parameter. So A is 0.24, light is 540 nanometers. Now note, I can convert 2.24 millimeters into microns, so it's now 240 microns, and I can convert nanometers into microns, which is 0.54, which gives us an ND max value of 444.44. Clearly that is a very large number, so there are a lot of minimas and maximas. Plot the relative intensity. There should be 444 minimas on one side, and that 0.444 is just almost at the maxima. So if I start counting these, the number of minimas is 2nd, so it's 2 times 444, which gives me 888 minimas. So when I look at the maximas, it's typically 2nd minus 1, but note, because of that 0.44 being close to the maxima, I'm going to count that because it looks like a maxima at that relative intensity. So then I get 889 maximas. Locations and the relative intensities of the secondary maximas follow the approximate path difference equation. A sine theta approximately equal to nc plus 1/2 times lambda. Solving for sine of theta, I then get nc plus 1/2 divided by the diffraction parameter of 444. The angular locations are, for theta 1, it's going to be the sine inverse of 1 plus 1/2 divided by the diffraction parameter, gives me an angle of 0.193 degrees. So if I replace this with theta 2 and theta 3, or I replace the 2 and the 3, I get 0.322 degrees and 0.541 degrees. The locations on the screen are given by y1 equal to d tan theta. So for y1 and theta 1, I get a distance of 1.01 centimeters. For y2, I get 1.69 centimeters. For y3, I get 2.36 centimeters. Relative intensity is a function of the phase alpha, where alpha is equal to pi a sine theta divided by lambda. The path difference, or the approximate path difference equation, we know that has to be nc plus 1/2 times lambda. Substituting this in, I end up with alpha being nc plus 1/2 pi, so therefore for nc starting with 1, I get 3/2 pi, 5/2 pi, 7/2 pi. Now have the alpha location of the first, second, and third maxima. Plugging in these alphas to the relative intensity, I then find that the relative intensity of the first is then sine of alpha 1 divided by alpha 1 squared, which would then be sine of 3 pi over 2 divided by 3 pi over 2 squared, and I get 0.0451. Now if I repeat the same process for 2 and 3, I get 0.0162 and 0.00831. What do these values mean? Well, if I look at I relative of the first maxima, I get 0.0451. That means that the brightness of the first maxima is 4.51% that of the brightness of the central max. In other words, this is quite dim. So for relative 2, it's 1.62% of that of the central max. For the 3, it's 0.831% of the max. So if you start off with the central max that's not very bright, these will be quite dim and hard to see. C. What is the relative intensity, angular and screen locations exactly in the middle between the central maxima peak and the first minima? This question has been changed from what was first listed. Looking at the relative intensity plot, what you see here is that the first minima is at pi, the central max is at 0, so smack in the middle is then pi over 2. The phase alpha must be pi over 2. Now note, that has to be written in rads, because that's the units of alpha. And so that's pi a sine theta divided by lambda, so now I could solve for that angle. Solving for theta here, note that the pi's cancel. Now I have theta equal to the sine inverse of 1 over 2 times the diffraction parameter, which is equal to 0.0645 degrees, a very small angle. Screen location, which is y equals to d tan theta, is then going to be 3 meters times the tangent of that angle, which gives me 3.38 millimeters. Its relative intensity is I relative at alpha equal to pi over 2. So plugging that into our relationship, we get 0.405. So the relative intensity then at this location is 40.5% as intense as the peak intensity.